So, Alice will tell us about spectral analysis of metallic glasses for X-ray absorption fine structure spectroscopy.
Am I good? Okay.
You're good, go ahead.
So hi, I'm Alice, as most of you know, and I've been working on my senior project with Professor Carter of the Material Science Department from across the quad. And my project has actually been a very physicsy one too. I'm eventually working towards finding the structure of metallic glasses by X-ray absorption fine structure spectroscopy. So before we even get started, this project wouldn't have been possible without a lot of people. A lot of physics professors have helped me on this project, whether they know it or not. I've been utilizing the knowledge I've gained from quantum mechanics, E&M, computational physics, and my lab classes. And here are the professors that taught me all the critical pieces to put this entire project together. In addition, Professor Kahneman and Professor Rule, where's the point? There it is. Professor Kahneman and Professor Rule have been specifically helping with this project, and I've been lucky enough to talk to Professor Lambrecht about some of the basics of XAFS. Professor French and the rest of the SDLE and mesoscience groups have also been giving me a lot of guidance with the project, and SDLE has been nice enough to offer me a workspace to work this past year on the quad. Computationally wise, I've been using the high performance computing cluster here at PACE, and this will all make sense later, but Rachel, anyways, this will all make sense later, but the experiment has already been performed by Trudy, Aaron, and Professor Carter, and Rachel has been helping me with the molecular dynamics and more the theoretical side of the project. So I just wanted to take a moment to thank all these people. And let's get into the project. So in physics, there's theoretical side things, and then there's experimental stuff. My goal is to eventually be able to model the structure of these three materials independently through theoretical and experimental means, and compare their results via computational methods. I've decided to use Python as my main coding language for a variety of reasons. Oh, wow. So, much like computational physics, computational material science is a branch of material science that's gaining traction recently. And I don't know how many mechanical engineers there are in the group, but I like to think of it as, imagine having to design a mechanical system without SolidWorks, which is a 3D graphical user interface software that allows you to build parts, assemble the parts to make sure they fit through an assembly, and ultimately run simulations on the parts and the assembly to verify that your thing holds up in a real-life environment. All this from a software that allows you to change the dimensions of your parts freely and without having physically built anything. So for a mechanical engineer, this SolidWorks file is just as good as, if not better than, this final product. Imagine having to build something like this without SolidWorks. That's where material science is at right now. We rely heavily on lab data for our experiments, and some simulations are simply too big or just not computationally feasible to do. One of my material science professors has actually even brought this up in class a lot of times, stating that the increasing computational power will allow us to conduct experiments that were simply not time feasible or money feasible to do in a lab. So my project is part of this whole thing, to build a material works that is able to solve Schrödinger's equations, much in the same way that SolidWorks solves Newton's laws. So honing in more specifically on my project, I'm going to be focusing on metallic glasses, which, as you can see from this Ashby plot, where's the pointer? The metallic glasses are up here in the black circle, and metallic glasses have a higher yield strength and fracture toughness than most other materials. Here, yield strength describes how well a material holds up under pressure, and fracture toughness is a measure of how hard it is for a crack to propagate in a material. So with these metallic glasses, in the computational material science field, there's still actually some debate on how the atoms interact on the atomic level. That is the theory I'm trying to verify with my entire project. To verify the theory, we feed in something, a three-dimensional representation of this one-dimensional Leonard-Jones potential into a molecular dynamics software, which is a software that allows us to model materials. So the software that I've been using is LAMPS, mainly just because our group members have experience with it. And what it does is it takes in a potential file, and then it runs basic F equals ma Newton's laws equations to determine where all the atoms in a solid like this would be at each given time step t. And after having incremented a number of time steps and reached the t max, it returns out a file that contains all the positions and whatever properties you wanted to calculate for each individual atom. And so in a visualization software, we can model something along the lines of this. You'll see this graph more in the future. So to make sure everyone's on the same page, the theory that we're verifying for these three structures is the potentials on how the atoms interact. And we're trying to compare our model to their real-life counterparts through the experimental data and comparing via computational techniques. Okay, so before I move on to more of what the project is, I wanted to cover some background to make sure everyone is on the same page. So starting off real simple, in material science, a crystal is simply a solid with its atoms arranged in a crystalline fashion, well, in a periodic fashion. And then once we relax the long-range order of these solids, we get glasses. So a metallic glass is essentially a glass or amorphous material with its atoms being metals of the metallic kind. So since it is obviously not convenient to have to know where each individual atom is at any given point in time, in material science, the material science community often uses the real distribution function, or RDF, to describe where atoms are in relationships to each other. For the more mathematically minded audience in the group, the RDF is a probability distribution function, pi of x, where pi of x represents the probability that any two given atoms are separated by a distance x. Okay, enough math and material science. Let's jump into some physics. That's what we're all here for. So X-rays come in from the left and interact with this material. I should probably just move up here. X-rays come in from the left and interact with this material. Let's say the X-rays hit this blue atom here. Below the edge jump energy, how do I do this? Below the edge jump energy.
I would stand further back, I think, wherever you come up and walk around.
But then there's like animations and fun things.
Okay.
Okay, yeah, whatever. Below the edge jump energy, this X-ray does not have enough energy to excite a core electron, and so very little absorption occurs. Once the X-ray has enough energy to excite the electron, it will. The core electron gets excited into the conduction band, and its wave function starts spreading out. This wave function interacts with nearby atoms, and so we get a wave function that looks more like this. So if the wave function constructively interferes at the central atom, we get a higher probability that the electron will be able to relax, re-emitting a photon in the process. And if the wave functions destructively interfere at the central atom, we get a lower probability that the electron will be able to come back and relax. So this probability is ultimately what we're measuring with this absorption curve. As you can imagine, depending on exactly how far apart the atoms are, the probability changes, and so does the absorption curve. This absorption curve shown at the bottom left here is a typical XAFS or XAFS plot. XAFS stands for X-ray absorption fine structure. Right above the edge jump energy, the excited electron does not have the energy to travel very far and interact with the nearby atoms. And so we could only get the chemistry of the material. But once the excited electron has more energy to travel further, we can start getting the structure of the material out in the XAFS region. These XAFS wiggles are described by this equation. So since I'll be coming back to this equation throughout the rest of the talk. I don't want to waste that much time on it here. This equation really is at the core of my project. So for now, I just want you guys to know that I'm referring to this monster whenever I say XAFS equation. Got it? Cool. Let's move on to the details and what I've actually been doing this past year. So as I've stated before, the main goal of this project is to compare theory and experiment through computational methods. My eventual goal is to be able to get these 3 glasses, but in order to find some of the parameters to fit into the XAFS equation and to verify that my techniques actually work, I need to run the analysis on the solids, on the crystalline solids that build up the glasses first. So for my senior project, I've decided to focus on nickel. Here is the model that you've seen before for nickel. And once we get the pairwise and triplet-wise distances, we can plug these values in as R sub j's to the XAFS equation. Here, all the other factors all serve as correction factors. Since the distance the electron travels is not quite the same as interatomic distances. So these factors take into account things like the probability that the electron will actually scatter when it hits a nearby atom, the phase shift as it scatters, delta J, the probability is Fj, by the way, and the fact that, as I mentioned before, the electron's not quite traveling the center-to-center distance when scattering off atoms, and a lot more terms account for a lot of other stuff. And so in a computer file, all these terms are stored in instances of paths. Here on the right are some viable paths. The green and purple ones are actually the same path with a degeneracy of 2. So the green and purple ones are actually what you would normally think of as a path. The core electron, the center electron, gets excited and comes out, bounces off a nearby atom, and returns. But keep in mind that something like the blue path is also viable. A path does not necessarily have to be between 2 atoms. So in computer science terminology, all these path files are stored as instances of a path class. These individual instances all contain variables to fit to the XAFS equation independently, and each path is just what one of these R sub j's or N sub j's. So as you can imagine, the amount of variables adds up quick, and so finding the correlations between the variables become important pretty fast. But that only becomes a concern once we're done cleaning out the experimental data. So let's move on to that. On the left here is a plot of our raw data, and that you have seen. And if we fit a polynomial to the post-edge data up here and set the polynomial value to a y value of 0, you get the features shown in the middle plot here. Here the x-axis is also shifted, so by this simple equation. So what the equation does is it converts between the energy E of the electron to the momentum K of the excited electron. The energy E of the X-ray to the momentum K of the excited electron. Once we get the momentum K space data, all we need to do is a Fourier transform to get it into the position R space. For the more technical folks in the group, momentum K space is also the reciprocal space, and the position R space is also the real space. But I like to think of it as momentum and position just because that's the intuition I've developed from quantum mechanics. And so the chi-k data really is ultimately the data that we're fitting to this equation, but chi-r just provides a more intuitive way of checking. Since r has a physical value, r is correlated to the distance between a pair, a triplet, or any other group of atoms. So here is the near final comparison for nickel. After accounting for the pairs in the structure that I modeled, we generated this radial distribution function for nickel. And for the experimental data, I've been able to match the paths to the experiment pretty well. So the red is the fit and the black is the experimental data. So as you can tell, everything's coming together pretty nicely, with one small caveat though. The paths here were generated from an online model. So to fully finish up nickel, I need to be able to convert my own radial distribution function into path files that I can ultimately use to feed into to fit my experimental data. So after that deep dive into the experimental and theoretical fronts, it's time to take a step back. All of this is ultimately going to be used to verify that our current theory on how atoms interact within glasses, to verify our current theory about the interactions of atoms within glasses. And to do this, I am running analysis on the crystalline solids first to verify my techniques, and also being able to find some parameters to feed into the XAFS equation for glasses. So with that said, the future of the project is relatively clear. I'll finish up nickel, use the techniques I've developed for nickel to analyze the other crystalline solids, and hopefully be able to use those same techniques to analyze glasses. And ultimately, to quote Professor Rule, we are going to confront current theory with our experimental data. The theorists aren't going to like it, but confront experimental data with our current theory. So that basically wraps it up. In summary, I'm taking theoretical models and analyzing our experimental data and trying to match the structures the two sides of the coin generate and see whether or not they match. Okay, cool. References, and thank you, questions. Also, the physics department needs to pick up their game. I got this from the material science department the other day. Anyways, questions? Hi, John.
You have medication.
Questions?
Yeah.
There was a peak in the experimental data that wasn't reproduced in the calculation. Do you have any? Yeah, do
Oh,
you
you
have
mean
any
like
speculation about
this
what that
little
is?
bump?
Mm-hmm.
I think it's just the fact that my fit doesn't go all the way out there. But so the modeling of the paths actually only, I believe the way I did it only goes up to 5 or maybe 6. So I mean, if it goes up to 6, I don't exactly know what that bump is.
The paths that you used are those
Yeah, so these
just,
paths are from the
one
online.
and back paths, or do they include scattering off two different?
Oh, these
Atoms,
paths?
yeah.
They include everything, so triples and even 4 scatterings, because so in XAFS there's like a magnification effect. If you go from like one atom to the next and then to that and come back, there's some sort of magnification effect that I don't know why the physics works that way. You tell me. But Lambrecht, yeah.
So this is just FCC nickel, right?
Mhm.
So should those peaks be just like the shells, like 12 first nearest neighbors and 6
No,
second
because
nearest neighbors
so-
and so on? Or why is it not looking like that?
Yeah, so the idea with this model is it was generated from at room temperature. So the nickel atoms are going to have, more energy to be excited to leave their lattice sites, essentially. And then so you get like a little Gaussian-ish distribution of all the,
Right, so that determines the width of these things.
yeah. So,
I don't remember all the nearest neighbor numbers in the shells, but I thought there's 12 first nearest neighbors in FCC, right? And then second nearest neighbors, there are only 6, I think, but it looks like these peaks are.
oh yeah,
different by
so
a factor of
this
4,
is
so
actually
should-
a density. It's not exactly the number. It's so I don't exactly remember how the software does it, but it's something along the lines of you take the actual number and you divide it by like the surface area of the sphere. So it's like kind of a density. So as you move out, it will decrease the,
I see, okay, that's what I see.
The surface
Yeah.
density.
yes,
Okay,
something along those
okay.
lines.
I see. So the fact that you solve all these paths,
Mhm.
that means that you include not just kinematic one-way scattering, but multiple scattering.
Mhm.
And how many scattering events, or how, how does this converge? How many paths does one need?
Honestly, I don't know, but from the literature I've been reading, you can get pretty close with like maybe 50-ish paths for like a lot, most materials.
50 or 15?
50.
Zero.
But then also, since this is a crystal, for this fit actually came out to be 16 or maybe 17 paths, 16 paths. So as you can see, you get most of the structure covered by just a small subset of the paths. And also, so with the XAFS equation, you probably know this better than I do, but with the equation, since there are, actually, I have a better slide for that. Since there are these exponential decay terms, especially the lambda k, that depends on how far apart, like, so the longer your path is, the less it contributes to the overall signal.
So what are the approximate values of lambda k?
Oh, I don't know. Like, I think for this specific nickel system, it turned out to be around 10, right? 5 to 10
That was you, that's,
angstroms.
thanks for this.
Yeah.
So Richard, so why can you take the terms from your crystalline solids that are in this equation and use them for your glass? What is your assumption that allows you to be able to do that?
Good question. So yeah, a lot of these terms are either theoretically dependent or experimentally dependent. And the idea is, since we ran the experiment on the same apparatus, we can find some of the experimentally dependent parameters, I think the most notable of which is the amplitude reduction factor. And so once we find the amplitude reduction factor, we're assuming that the apparatus didn't change magically when we swapped out our samples. And that allows us to be able to feed this into the XAFS equation to find the RJs for glasses. And then also things like delta, the phase, come from more theories, the more theoretical side. So that eventually will be fed in to the glasses from just generated data that from the crystalline models, since it is.
The path for the glass and the path for the crystal are different. So what assumption do you have to be able to use the phase, for example?
Well, the phase is only dependent on the atom that the electron bounces off of. Yeah.
And it confuses me with these paths, because I thought this equation was derived from the assumptions of kinematic scattering. Just like you do X-ray scattering, you assume only one scattering, and you don't really do multiple scattering. You sum over each shell of image. But you say now that you can apply this to sort of taking paths that go back. I thought you would actually have to do advanced structure calculation to get the multiple scattering, but I'm not sure.
No, I mean, I think that equation is quite deceptive in that context, because F and delta we would ordinarily think of as being the real and imaginary parts of the scattering function, but if you have a longer path, it's the real and imaginary parts of the product of the scattering functions. I'm also a little concerned that there might be differences for S-wave scattering and other non-S-wave scattering.
There's no angular momentum.
Maybe I should stop talking. Long
Yeah,
ago.
I think the angular momentum part of it shows up with the Zane's function, where you're trying to look at
So
S
you're
and P
saying
type orbitals. This sort of assumes that it's it's just
Right,
spherical, where if you're in the Zanes, it's
So you're
interacting with
Then you have to
SPs,
do
so
that.
then you have to deal with
You're
that.
at- Well, the way I would say it is you're at high enough energy, that
Yeah.
basically S-wave scattering and
Yeah.
single scattering dominates.
Yeah.
But that's why I'm actually confused about the multiple scattering path, because I thought this equation was derived in single scattering approximation.
Ooh. I don't know actually.
That's what confuses me.
Mhm.
Well, will the cumulative expansion terms be able to accommodate for some of that?
I have to look at them.
We'll find out at a workshop next month.
Hey.
Let's thank the speaker again. There could be lunches outside for, I think, 30 people, and there are 30 people here. So please, feel free to get a lunch and sit around and chat with our students.
No, please do.